Hello students, welcome to EPG Pathshala. I am Sunil Kumar from IIT Delhi. Today in this module, we are going to discuss about kinematics, kinetics, dynamics, inertia and so on. So the aim of this module is to learn about the following topics: the motion, components of kinematics, equations of motion, relative motion, kinetics, which is different from kinematics, then laws of motion, and then we will try to learn all these topics through some illustrations. So the first question is, how do you define motion? So in simplest terms, motion is the change in position of an object or particle or body with reference to a fixed point or fixed object with which we attach our coordinate system and measure physical quantities relative to it. Then motion can be divided into various kinds such as translational motion, rotational motion, vibrational motion and so on. Now, kinematics and kinetics, these two are different things. One should not just, one should be aware of the fact that these two are different things. In kinematics, we learn about the motion of objects without considering the causes of the driving forces behind them. Whereas in kinetics, we not only learn about the motion of the objects, but we care about the driving forces behind the motion and the reactions by the objects to the applied forces or to the external forces. So in kinematics actually, we learn about three things: statics, dynamics and inertia. All these three are basic ingredients of the study of kinetics. Observables. The physical quantities that we observe and measure can be divided into two main categories. The first one is scalar quantities. Scalar quantities are those which need only magnitude to describe them. For example, speed of a body, mass of a particle, temperature of a system, time, etc. So these are the quantities which need only the magnitude to define them or to quantify them. The other category is vector quantities, which are those quantities which need both the magnitude and the direction to describe them. For example, velocity, displacement of a particle, force, momentum, etc. All these quantities require not only the magnitude but also the direction. Now, components of motion. So motion, when you define a motion, you talk the motion in terms of various physical quantities. What are those physical quantities? It can be position of an object or of a body which is in motion. It can be distance, it can be displacement with reference to a fixed point in space. The motion can be described in terms of angle, change in angle. Momentum. The momentum can be linear momentum or angular momentum, depends what coordinates you are taking. Then speed. What is the speed with which the body is moving? Or velocity. These two are different quantities. Speed is a scalar quantity and velocity is a vector quantity. Then acceleration and force. You apply certain force to a body. What acceleration it produces in the motion of that object. So you can actually describe the motion of that particular object in terms of acceleration or force acting on it and so on. So you have these components which actually are used to describe motion of a body or a particle. For example, you have these red blood cells in your blood. So they are always in motion. Now you observe closely one red blood cell. Sometimes it is moving along a linear path, sometimes it is taking a different path which is different than linear. So it has not only linear momentum, it has not only the speed, it has velocity also, because it is changing the direction of its motion. With respect to a fixed point, it has certain displacement. Let's say you start with a very specific red blood cell. Let's say start from heart, and then after some time it goes to different parts and comes back to heart, for example. So you explain that motion of that particular red blood cell in terms of these components which I just described. Components of motion. The vector components of motion are expressed in a given frame of reference, which is generally, in most of the cases, the Cartesian coordinate system. The instantaneous position coordinates of any object are written in terms of x, y, z, for example, in three-dimensional space, or in the xy plane, the coordinates are simply x, y. In this picture here, you see the positional coordinates of a body which happen to be at point P at certain time t, and at a later time, let's say t prime, it happens to be at point Q. So the position vectors from the origin are shown by the arrows. So the coordinates of first position P are simply x1, y1, and similarly the position coordinates for the second place, which is represented by point Q, are simply x2, y2. So the basic idea here is to have a reference frame so that you can describe the positions of a moving body. In this particular slide, we try to stress the point that we have to be careful about the description of vector quantities. I mean, sometimes the physical variables may sound similar, but their meaning turns out to be different. For example, when we measure distance and compare it with displacement, we have to be careful that distance is simply a scalar quantity. On the other hand, displacement is a vector quantity. So when we measure displacement, we have to give the direction in which it is measured. Similarly, speed and velocity of a particle. Speed is a scalar quantity. On the other hand, velocity is the vector quantity. So there is a difference in terms of description of these two. The second one, which is velocity, needs to be defined with respect to its direction also, not only the magnitude. In this picture here, a particle is moving on a circle of radius 5 centimeter. So with respect to the center, the direction of the particle is always changing. So we have to measure from initial point after certain time t, what is the displacement, and that we have to tell whether it is clockwise or anti-clockwise. On the other hand, if you want to talk in terms of distance from the center, it is simply 5 centimeter, which remains constant always in this particular example. To categorically see the difference between speed and velocity, this slide points out the three basic differences between the two quantities. In case of speed, it is simply the distance covered per unit time. On the other hand, velocity is the displacement per unit time. The second difference is speed can never be 0 or negative, but velocity can be 0 or negative as well. The third point is speed is a scalar quantity, that is, it has only the magnitude but no direction associated with it. On the other hand, velocity is a vector quantity, that it has both the direction and magnitude associated with it. So the take-home message from this slide is that we have to be careful while describing physical quantities. Some physical quantities are scalar, which have only the magnitude to describe them, but some physical variables or quantities are vector quantities, which need both magnitude and direction to describe them. Let's see some definitions. Linear velocity. Linear velocity is nothing but linear displacement per unit time. Angular velocity is angular displacement per unit time. Acceleration is change in velocity per unit time. So accordingly you can see the linear velocity has dimensions of meter per second in MKS system of units. Angular velocity has dimensions of radian per unit second, and similarly acceleration has dimensions of meter per second square in MKS system of units. So there are units of measurement involved here, which we already at some point of time talked about. MKS system of units, where meter, kilogram and second are the basic units. Second popular system of units is the CGS system, where C stands for centimeter, G stands for gram and SS stands for second. So time, distance, angular displacement, velocity, acceleration, all these physical variables are actually some of the most basic physical variables which are used to describe other physical variables. So equations of motions. In kinematics, the motion of objects under constant acceleration A is governed by three equations. The first equation is about estimating the velocity at time t. Mathematically, it's v equal to v naught plus at, where v is the velocity at time t that you are interested in to know. V naught is the initial velocity and a is the acceleration, constant acceleration. Second equation is to find the displacement from t equal to 0 at t equal to t. What is the displacement? So mathematically the equation goes as r minus r naught equals v naught t plus half at square. And the third equation is v square equals v naught square plus 2a r minus r naught. So here you can calculate v if given v naught, a and r. So these equations are valid for any dimensional problem. These are valid for one dimensional problem or two dimensional problem or three dimensional problem. As an example of equations of motion, here we saw the projectile motion. What is it? It is basically the motion of a body thrown out in the air at an angle theta with respect to the ground. So during the whole projectile path, which happened to be a parabolic path, the velocity of the body keeps changing due to the balance between the applied force and the gravitational force. The whole motion of the projectile can be modeled accurately following the equations of motion that we just described in the last slide. So here the particle which is thrown out at an angle theta, or theta naught here in this picture, with an initial velocity v naught, reaches a maximum point or maximum height where the theta with respect to ground is 0 and the velocity is 0, and the total energy the particle has at that point is only the potential energy, because the velocity is 0, so kinetic energy is 0. And from this point the particle starts coming down towards the ground because of the gravitational force acting on it. And then at the moment the particle hits the ground, it has certain velocity. This velocity and the total time taken in the whole motion can be calculated actually using the equations of motion. Let's see an example from kinetics. Here in this slide, we would like to study the motion of an object having mass m, which is under the influence of four forces here. The first force acting on the body is the weight of the body itself, which is Fg. The second force on the body is the normal force due to the ground. The third force is the forward force Fm, which is applied externally, and the fourth force and the last force is Ff, that is the force which gets developed due to the motion and the friction between the body and the ground. So when all these four forces are balanced, there is no net motion. Whatever is the direction, in the case of unbalanced forces, the particle or the body starts moving in that direction. Newton's laws of motion. So these laws by Newton are applicable only for inertial frame of references. These laws actually describe the motion of an object under the influence of forces. The first law, which is the law of inertia, says that an object will remain at rest or continue in motion unless acted upon by an external force. The second law, or the law of motion, states that acceleration produced by an externally applied force is proportional to the net applied force, and the proportionality constant is the mass of the object. The third law of motion, or the law of action reaction, states that every action force on a body has equal and opposite reaction force from the body. Let's see an example of the first law of motion, which is law of inertia. Suppose you are riding in a car and you step on the brake suddenly. What would happen? The following situations arise. First, inertia keeps you moving forward at the same speed as the car was moving. Second, you will keep moving until something stops you. This might be the car's steering wheel or dashboard or windshield. And if you are using a seat belt, it will keep you from moving forward when the car stops suddenly. So why do you move forward when the car stops suddenly? Because you are moving with the car, so you have the same inertia, and that inertia wants to remain the same when the car suddenly stops. So because of that, you keep moving forward even if the car has stopped. Let's see the example of the second law of motion, which is law of acceleration. As the definition goes, the force acting on a body is simply mass times the acceleration produced by the force, or mathematically F equal to ma, where m is the mass, a is the produced acceleration. In this example, you have a car which has got mass m equals 500 kilogram. You multiply that with the gravitational acceleration, you get the force, which is gravitational force in terms of Newton if you are using MKS system of units. The force, the forward force F1, let's take it to be 500 Newton, and the frictional force, which is opposite to the direction of motion, let's take it to be 200 Newton. So there is a net force in the forward direction, and because of that net force, there is an acceleration in the forward direction. For this example, the acceleration produced by the net forward force turns out to be 0.6 meter per second. As an example of the third law of motion, let's see two objects tied with the help of a rope. One object is sitting on a flat surface, and through the pulley, the other object is hanging. So because the other object is hanging, there is a force F2 acting on it, which happens to be the gravitational force. M2, if M2 is the mass of that particular body, the M2 times G is the force acting on it. And because the rope, single rope is tied between the two objects, there is a tension T developed. The direction of that tension is according to this picture. So if the whole system is not moving, meaning that the net force on the whole system is 0, then the force F2 has to balance T, or T has to get balanced by F2. Similarly, the net force on object or body M1 has to also be 0. So accordingly, the T, which has the direction as shown, has to get balanced. So relative motion also is very important thing to know. Our observation of motion of objects depends on our point of view or on our frame of reference. No motion can be called absolute because something at rest for you may be moving for others and vice versa. So every motion is relative and depends on factors such as frame of reference and state of motion of the observer. Let me explain this using one or two examples. So you have the moon rotating around the earth in a circular orbit. Now for an observer which is on the earth, he feels that the moon is rotating around the earth in a circle. Now if the same observer goes to the moon and looks at earth, for him not the moon but the earth is rotating around the moon in a circular orbit. So it all depends on the reference frame, in which reference frame you are talking about. For different observers, the motion of a particle or motion of a body can appear differently. So you have to be aware of the frame of reference. So relative motion has very important, it is very important to be understood here. Let's say we have another example. Let's see another example of electrons in atoms. What they are doing? You have very heavy nucleus, and the way the electrons, which are very light compared to the mass of the nucleus, they are rotating around the nucleus in approximately elliptical orbits or circular. Some people in Bohr's model it is circular orbit. So for the electron, if you are moving with the electron, then you feel like the nucleus is moving around the electron. But if you are sitting on the nucleus, then the electron is moving around you. So therefore it all depends on the frame of reference. What is your fixed point? So for different observers, the motion of a single body can appear differently. That is the idea of relative motion. As an example of relative motion, let's say a plane is flying with a linear velocity of 500 km per hour against the wind velocity of 25 km per hour. This plane would appear to have a resultant velocity of 475 km per hour to an observer on the ground. So pictorially or vectorially, the two velocities, one of the plane against which the air is blowing, the resultant velocity of the plane will have a smaller magnitude, which can be immediately seen from this vector sum or vector addition of the two velocities. Similarly, if the plane is moving with the wind in the same direction as the wind, then the velocity of the plane that the same observer estimates on the ground is now going to be the vector sum of the two velocities, the plane, the velocity of the plane, and the velocity of the wind. So the resultant vector, velocity vector, has larger amplitude, which is larger than the two individual amplitudes. This slide explains the meaning of linear momentum. Let's say a body of mass m is moving with velocity v. Then the linear momentum is defined as p is equal to m times v. Linear momentum is a vector quantity that has specific direction and magnitude. So here in this picture you have the body of mass m moving with velocity v. So this velocity vector has a certain magnitude, which is represented by the length of this arrow, and the momentum, linear momentum, also is a vector quantity which also has a magnitude and direction. Because p times mv, in this expression v is a vector, m is a scalar quantity, so the resultant of the two, p, also is vector and has the same direction as v. But because the magnitude is higher, larger than the magnitude of v, so you have the resultant vector representing p having larger magnitude or length in this case, then the velocity, then the magnitude of the velocity. Let's now see linear momentum through an example. How do we understand it? Let's consider a body of mass m moving with velocity v, hitting another body of mass m by 2, which is at rest. So in the first case, when the bigger body is moving with velocity v, hits the other one which is smaller, having mass half of the first one, but at rest. After the collision, both of the two bodies start moving. And from the law of conservation of linear momentum, we can estimate what velocity each body is going to have after the collision. Now let's see how do we understand angular momentum. For this, let's consider a body of mass m that is moving on a given path with respect to fixed point. Then the body is said to have an angular momentum along an axis which is perpendicular to the plane of motion and passing through the center or the fixed point. The direction of the angular momentum, if we can represent it by p theta, depends on the direction of the motion. So mathematically, p theta equals the cross product or the vector product between r, which is the displacement vector with respect to the fixed point, and p, which is the linear momentum. So the angular momentum is obtained by the vector product between r and p, and the magnitude of this vector is simply m times v, which is linear velocity, times r, which is the distance from the fixed point around which it is rotating or it is moving on a path. In this peculiar example of the system of planets, in our solar system, the planets are spinning around their axis and in an orbit around the sun. The total angular momentum of each is the sum of the orbital angular momentum and the spin angular momentum. And the total angular momentum of each planet or natural or artificial satellites is always conserved. So in this picture you see at the center you have the sun, around it you have various planets, and around each planet there are satellites which are called natural satellites. Around Earth there are, other than the natural satellite which is moon, we have many artificial satellites which humans have sent in the space. So as a whole, the whole system has the angular momentum conserved. If anything has, because of collision or because of transfer of momentum, higher angular momentum, then immediately at some other point or some other object there is going to be loss of angular momentum, so that the overall angular momentum is conserved. So this is the natural law, that we always have the conservation of not only energy, but here in this particular example, through this example we try to explain that the angular momentum also is conserved. Let's discuss the angular momentum of electrons in an atom. The electrons in an atom are moving in orbits of fixed energy, which can be represented in the simple Bohr's model as circles or in 3D spheres. The electrons also have spin angular momentum because of their spin around their own axis. Quantum mechanically, the electronic motion around the nucleus is such that the total angular momentum is conserved. So if I is the moment of inertia, which is shown here, and omega is angular velocity, then once you have the spin and the orbital angular momentum, there is a total angular momentum which is the vector sum of the two, has an axis passing through the center, which happens to be the nucleus in this example, and one can actually estimate, depending on the knowledge of mass of electron and the forces between nucleus and the electron and the size of the orbit, one can estimate what kind of angular momentum, total angular momentum is there in an atom or the electron in an atom. Let's see some problems for practice. In first question, suppose a man measures his weight in an elevator moving in upward direction with acceleration a. What would be the apparent weight as measured by the weighing machine? Assume the mass of the man as m equals 65 kg and the acceleration of the elevator as 8 equals 5 meter per second square. So use the laws of motion to find out the answer, and the answer is 962 Newton. But as I said, use the laws of motion to find out the answer, whether you get the same answer or not. Here is another problem for practice. In this problem, a body moving on a curved path has a velocity of 30 meter per second at an instant of time when it is heading towards north. After 20 seconds, its velocity was found to be 40 meter per second towards the west. So the question is, calculate the average acceleration due to this interval. So to solve this problem, you have to use the equations of motion and find out not only the magnitude of the resultant acceleration, but also in which direction the body is moving. So the correct answer is 2.5 meter per second square in a direction which is 37 degrees south of the west. So you have to use equations of motion, the three equations of motion, to find out the answer and try to see if your answer matches with this. To summarize, we learned about motion of classical objects in this module. The first thing that we learned was when we discuss about motion, we have always a frame of reference. Meaning, if you are describing the position or this velocity or any quantity, it has a frame, it has a reference point, reference value, reference quantity. With respect to a reference quantity, you always define that physical observable. Third, kinematics is a study of a state of the motion without asking for the causes or driving forces behind it. So some body is in motion, you just study its motion without worrying about the reasons why it is in motion. When it is in motion, obviously there are forces which are acting on it, some driving forces. But in kinematics, you are not worried about those forces, those reasons which cause the motion. What you worry is that if it is in motion, you would like to find out what happens after certain time. If you know the initial parameters, if you know the initial values of that particular observable, for example. On the other hand, kinetics deals with not only the details of the motion, but also the reasons behind the motion, meaning that the complete detail of the motion is the study that is done in kinetics. So there are three equations of motion in kinematics that we learned, and these three equations actually govern the complete motion of moving objects. And then in kinetics, where we worry about the forces also, the driving forces also, there are three equations of motion. We call them laws of motion, which involve the concepts of force, inertia, and action-reaction. These laws are called Newton's laws of motion and hold true only in inertial frame of reference. So in this module, we try to learn about not only kinematics but kinetics as well, and the basic emphasis was to have a clear picture about the difference between these subjects, which are again part of the study of classical mechanics. So the aim of the module is clear that we should be at the end of this module we should be clear about the difference between the study of kinematics and the kinetics. Thank you.